Our next talk now is from Farhang Radjai at the University of Montpellier, and he's going to talk about Elasto-plastic behavior of polyhedral particle packings. So over to you, Farhang.
Thank you very much. Thank you. Good afternoon to everybody. I think now you can sit back and take a rest after. What I'm going to present is much simpler than on-knots, rack drops, toroids transforming into hollow spheres, and so on. So I'm going to talk about elastoplastic behavior of polyhedral packings of polyhedral particles. First, let me thank the organizers for inviting me to give this talk. I apologize that I was unable to attend this interesting conference. Although Montpellier is not far from there, due to family emergency, and thanks to Simon Cox, who assisted with the Zoom connection, actually. So this talk will be mostly about packings of polyhedral particles. So this was mostly done in the framework of the thesis work of Duc-Chung Wu here in Montpellier, and in collaboration with Jean-Yves Delaine, Lassana Marcid, and Vincent Richaufeau. Polyhedral particles are very common in nature. It's due to their origins. We have rock fragmentation, which produces mainly polyhedral-shaped particles, mineral crystallization, and also I think many viruses and so on have also polyhedral shapes. Very little is known about these packings, mainly due to the variability of the shapes. So number of faces, edges, and some geometrical properties such as elongation and so on can change a lot in different contexts. And in general, it's difficult to characterize what we generally do for sphere packings. For example, packing properties, random closed pack structures of these things, space filling properties, and the microstructures such as coordination number, local ordering, anisotropy, and the relation with mechanical behavior such as shear strength, elastic moduli, and so on. So I want just to show you some of the past simulations using the discrete element method that we did in the past. I think Ken talked about this morning, about this discrete element method. These simulations were done using the contact dynamics method. So here you see packings of polyhedral particles with different number of faces. So from nearly spherical shapes with more than 500 faces down to tetrahedra with only 4 faces. And we have been interested mostly in the mechanical behavior. So here you see the shear strength. So Q over P here is the shear normalized deviator stress in sheared packing of these spheres for different number of faces. So the angularity is increasing. And you see for spheres, so down here, we have a peak value of the strength, which is here. And then for tetrahedra S8, here we have nearly 2 times larger shear strength. And it is not changing actually in a very in a linear way. I mean, with the number of faces, it is almost saturating the value of the shear strength. When we look at the packing fraction of the spheres, we have the packing fraction of random closed packings. So prepared with 0 friction. So basically with 0 friction, we reach when you pack particles, you reach the highest packing fraction, and so phi0 here is the packing fraction of these isotropic 0 friction packings. And you see for a sphere here on the left, alpha, when alpha is 0, it's spheres, we have 0.63, which we know is the packing fraction of a random closed packing. Then it increases as we increase the number, decrease the number of, we have a large number of faces, or we are deviating from a spherical shape by transforming the sphere into a polyhedron with a large number of faces. it increases and then it decreases again. So which is an unmonotonic change of the packing fraction due to the interaction between, the contacts between the points of high curvature and low curvature. So we have steric exclusions and steric inclusions, and we have here a competition between these two effects. But when we look at steady flow, the packing fraction in steady flow of these packings, we see that it is, apart from this difference between spheres and this polyhedra with very high number of faces, then we have nearly no effect of the particle shape, which is interesting because whatever the number of faces, you have always a packing fraction which is slightly below 0.6. But these are related to the plastic behavior. But I'm going to talk mostly about elastic behavior. So this recent work, mostly first maybe 2 words about the interactions between polyhedra, how we model them, then how we probe elastic moduli, how the elastic moduli evolve, and how they are related to the microstructure. So the important point when we model in the framework of discrete element method, the particle dynamic simulations, the polyhedral-shaped particles, or the presence of these extensive contacts, face-face and face-edge contacts, as here in A and B. C is vertex face contact, and this is, of course, a simple contact, single contact. But for extensive contacts, we have geometrical constraints which are different. And of course, this is a key for modeling the simulations. We can no more use here overlaps, geometrical, the volume, for example, of the overlaps to model the interactions. And I should also mention that from past simulations, we know that such contacts, face-face, face-edge contacts, are much less in number, but they capture strong force change, and so they control the packing properties. So face-face contact is actually not a single constraint, but 3 independent relative degrees of freedom between particles in the normal direction between 2 polyhedra. We have, whether you consider rotations or displacements, relative displacements of 2 planes, 2 faces, of course, we have, for rigid particles, we have at least 3 independent degrees of freedom, which have to be frozen when we have a contact. So we have, this is equivalent to 3 geometrical constraints. So of course, in practice, we may have more contacts. For example, here you see the contact between 2 pentagon-shaped faces. One is slightly rotated with respect to the other, and we have 10 contacts between the edges of these faces. But of course, when we look, in practice, only 3 of them. So the relative displacements between all these at each of these points can be expressed as a combination of the displacements of 3 independent displacements. So that's why we can consider a face-face contact as a triple contact. The same way for face-edge contacts, we have 2 relative degrees of freedom, and so 2 geometrical constraints, and that's why we can call it a double contact. So we can also define for a packing constraint number, which is the number of geometrical constraints per particle. So this is shown here for NS is number of simple or single contacts, ND number of double contacts, and NT number of triple contacts, NP is total number of contacts. And so we can define this constraint number for a packing, which of course is equal to the coordination number in the case of spherical particles. So in an isotropic packing, so with 0 friction, for example, the number of particle degrees of freedom is equal to ZC over 2, because ZC over 2 is the number of contacts per particle, actually, number of constraints per particle. For example, for frictionless polyhedra, we have 6 degrees of freedom per particle. So this is this should be equal to 6. So ZC should be equal to 12. For spheres, it's 6. For contact detection, we have a method which is quite fast, which consists in first transforming the polyhedra into spheropolyhedra. So as a Minkowski sum of polyhedra with spheres. So basically the geometrical lieu of all the points which are at a given distance from the particle surface. This is equivalent for polyhedra to a clump of sub-elements which are cylinders. As you can see here, cylinders, spheres for the vertexes, and the planes. So this can be decomposed like this. And so the contact detection is simply reduced to the detection of sphere, 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 plane, cylinder, cylinder, and cylinder, sphere contacts. And so it's quite fast. We did triaxial shear tests using the packings of this particle. So for the interactions, of course, here, this is not sphere, so we are not using Hertz contacts. So we are using simply a viscoelastic law at each contact point. And we use also a regularized dry Coulomb friction law. So we have two stiffnesses, friction coefficient, and of course, we can use different, in this work, we use different types of polyhedra. We used octahedra, icosahedra, dodecahedra, and spheres with the same diameter. For the simulations, we also use 3 periodic boundary conditions, so fully periodic boundary conditions. The samples were prepared by isotropic compaction. So we basically under the same pressure in 3 directions in a cubic cell with 0 friction. So we reach a random plus packing of polyhedral particles. So the highest packing fraction reached, of course, for spheres is around 0.637. For icosahedra, we find a slightly lower value, it's 0.632, and for dodecahedra, 0.648, which is larger than spheres. The samples are isostatic, and as predicted for isostatic packings, ZC is nearly 6. It's slightly above 6, it's 6.05 because of the finite pressure applied on the system for spheres, and a little bit higher than 12 for polyhedra. We did triaxial compression using these isotropic samples as initial condition. Here you see a snapshot, and the compression is applied in direction, so here Z direction, and the pressure P is applied in the 2 lateral directions. So basically, the symmetry is axial, so we have a transversely isotropic symmetry in this problem. So sigma 2, the 2 stresses along the 2 directions are equal to P, and generally we also have the 2 deformations, the 2 strains along these 2 directions equal together. So here you see the evolution of Q over P, but Q is sigma 1 minus sigma 3, so divided by 3, so the difference between the stresses, and P is of course the average pressure, and so Q over P represents the normalized stress deviator. Here on the logarithmic scale, you see the evolution of Q over P. You see that at the beginning it's 0, as it should, because it's isotropic, and then it increases and goes to a peak. And these are for, I forgot to say, we tested 4 different values of friction coefficient mu s. So from 0.1 to 0.4. So here you see in solid lines. So here we have, of course, many points, and the symbols represent places where we have probed the elastic behavior. So we have many, many more points. So these are basically the solid lines. And as you see for polyhedra here in solid lines, as friction increases, we have larger value of Q over P. It goes through a peak for each of them. So this is the stress peak reached at a strain of about 0.1. And then it is softening behavior, as you know, where the system is almost unstable beyond this peak point. So we have the same behavior for all of. For spheres, they are lower as expected, but it increases with friction, as you can see. Regarding the packing fraction, as you see, it's nearly constant for a long time. up to 1% of deformation because there are no rearrangements in this range. So the deformation is basically, there is no plastic deformation of the system. And then when we reach close to the phi decreases due to dilation. So we have a dilatancy of the system and phi decreases. And beyond the peak value, it reaches a nearly constant value as usual observed in this problem. Okay, now let's look at the evolution of elastic moduli. So how we prop, we can of course use the matrices and so on to evaluate the elastic moduli. It's easier to prop. So we have 16 points where we prop the elastic behavior. Why probing? Because we cannot use the tangent to the curve as value of this curve that I showed you as value of to evaluate the elastic moduli, because here the strains are too large, and basically we are looking at the change of state. We are not with elasticity looking at the change of state, but at the state at a given time. So the strain should be strain prop, or strain that is applied, it should be low enough in order to avoid the deformation or the rearrangements of the packing. So we have, of course, because of the symmetry, axial symmetry, we have 5 independent elastic moduli, Cij. And if we use Voigt's notation, we have this definition of the 5 elastic moduli. So C11 and C22 are the longitudinal moduli, C44, C55 are the shear moduli, and we have C12 and C23, which are the off-diagonal moduli. The bulk modulus is given by this. So we probe the elastic behavior in 2 different directions, so that we have enough information to use these equations to evaluate. So we apply delta epsilon, and we evaluate the variations of the stress. And so we chose an increment of 10⁻⁵, which is small enough, at least for before the peak, before the system is unstable, is enough for evaluating the elastic moduli. We have more equations. Actually, we have more equations than unknowns, so we can check the consistency of the results, especially this relation, which is imposed by symmetry. We check it, and we see that most of the time our error is below 1% in the evaluation of elastic moduli, except when we reach the peak. After peak, then the error can increase. It can go to up to 10% of error in the evaluation of the elastic moduli. I would, because we are going to look at the elastic moduli, we have normalized all of them with E star, which is defined from the normal stiffness of the contacts divided by particle size. So this defines actually the order of magnitude of the elastic moduli. So we will normalize all elastic moduli by this. So here we look at C11, the 2 longitudinal moduli, how they evolve. And don't look at the solid lines, because the solid lines, as we will see later, is the model actually. So the data are the symbols, and you see that for I'm showing only dodecahedra here for increasing friction, and we see that again in this range at the beginning, the elastic modulus is constant. It's because there are no rearrangements at all. So we are in the same state. It's not moving. So, and it is independent of friction coefficient. And from here on, when we have the state is changing, and so the elastic modulus is changing, but it's not changing in a simple way. As we see, this is decreasing, sometimes increasing a little bit, again decreasing. Here we see that it is increasing after this point. For spheres, we have the same thing. Altogether, the values for spheres are below. But you see that when we look, for example, for a coefficient of friction of 0.4, which is high coefficient of friction, for dodecahedra, the value of C11 can go below that of spheres, which is interesting because we expect that for polyhedra, it's always larger. C11 is larger than a sphere, but this is not actually the case. And for C22, we have, of course, also the same trends. So the values are different if you look at this. When we normalize the data by E star, you see that actually orders of magnitude are very close. I mean, we are really looking at the variations around 1 when we normalize by E star. For C55, C44, the same trends. For C12, C23, the same trends. So we can, and for K, the same trend. So here we see that again, for polyhedra, we have larger values of the bulk modulus. And so we see the same trends that I showed you for C11, for example. So let's now look at the evolution of contact network, because what we are interested is in to relate these elastic moduli to the contact network. And the lowest order parameters are the constraint number, ZC, which discussed about previously, and the anisotropy, because in triaxial loading, we are inducing a strong anisotropy into the packing. And as everyone knows, the anisotropy of granular materials, when subjected to well-defined boundary conditions, in homogeneous boundary conditions, let's say, is generally very well approximated by spherical harmonics. So if we look at the distribution of the orientations, omega, of contacts, or the vectors joining particle centers, neighboring particle centers, it can be quite well approximated by this. And here it's even easier because it depends only on theta. It's not depending on the, it depends only on the latitude and not the azimuth angle. So here is the vector, unit vector, which shows the direction or orientation of a contact. So this can be, and AC here represents the anisotropy actually of the contact network. This AC can be evaluated from the fabric tensor. So it can be shown that in this geometry F1, the principal values of this fabric tensor are related to AC, the anisotropy of the packing, and that's how we evaluated the values of AC. And so here you see the evolution of ZC and AC with epsilon Q, the shear strain. So ZC, as we have seen, is 12 because it's isostatic at the beginning. I mean, because it was prepared with zero friction. When we activate friction, then it can change. But still, with the same, when we add friction, again here it's nearly constant because there are no rearrangements. And when the plastic deformations begin, then ZC decreases a lot, from 12 down to 6, for example, for largest friction coefficient in the case of polyhedra, and for spheres from 6, the initial isostatic value, down to slightly below, around 5, 4.5, 5. And the values are, as you see, decreasing. ZC has lower and lower value as the coefficient of friction is increasing. So the connectivity of the particle network is decreasing, while at the same time, the anisotropy is increasing. So again, here the anisotropy is 0 at the beginning because of the isostatic state. And then when the plastic deformation rearrangements begin, they increase and go past through a peak. That is the stress peak that we have seen before, and then it declines. And so we have the same trend for spheres and for the polyhedra. So here you see a snapshot of the packing by separating between single contacts, which are in white, double contacts in blue, and triple contacts in brown. And you can see that initially, because it's isotropic, we have a kind of mixture of all of them, although the percentages are different. So we have much lower number. We have 14%, sorry, 14% of contacts which are triple only. And here is at the peak, slightly before the peak stress, and you see it's organized. We see the anisotropy of the packing, and we see that most of these strong force chains here, the thickness is proportional to the force, are oriented along the axis of compression. And so they capture actually the strong force networks. The triple contacts are capturing most of it, and also double contacts. But still we have a mixture. And here the number of the number of triple contacts is lower than initially. It's now 10% almost. So it was 0.14, now it's 0.1. So how we relate this evolution of the microstructure with the evolution of elastic moduli? Of course, we can first think of effective medium theory. So in effective medium theory, which has been already used, but maybe not for anisotropic system, it's mostly for isotropic packings. We assume that the material behaves as a continuum. And so the centers of particles are moving according to the applied strain field. For example, if we apply delta epsilon ij, the vectors, branch vectors joining particle centers would change like this. So n prime here is the orientation of the vector joining two particle centers. But we are interested, of course, in at the contact points, and at the contact points, the orientations are different. I called it here n prime actually, and so it should be reversed here. It's n and n prime, and but we check that actually they are parallel. So on the average, they are parallel. So in a way, we can use the branch vectors using the affine assumption to evaluate the local displacements at the contact points, not only at the branch vectors. From these displacements, we can write down the elastic energy increment per unit volume, which is written here, in which we have the three now values of the three stiffnesses, normal stiffness and the two tangential stiffnesses, or the tangential stiffness, and using NC, which is the number density of contacts, number of contacts per unit volume. And then we can derivate this energy with respect to different strains in order to get the elastic moduli. And here they are written, as you see, and this is K. So for K, we have no dependence on AC. As you see here, all of them are depending on AC, and but K is not dependent on AC. We get this expression, which is NC, the density of contacts multiplied by average value of the branch vector length squared times the normal stiffness divided by 9. This is a classical result, which is obtained for isotropic packing. So the isotropic value, expression of K according to EMT is the same as in an anisotropy. So the expression that we get for K here, you see that this is simply proportional to NC, but NC can be written like this. NC is ZC times phi divided by the volume of the particle, average volume of the particle. So phi is the packing fraction and ZC is the constraint number. And so in the value of K for EMT is a prefactor times E star, which is our reference modulus, times phi ZC. Okay, this is what is, but what do we see? So what we measure is K here as a function of phi ZC. This is the this line here, red line, is the prediction of EMT, and these are our data. So you see that our data are indeed linear. So that is something which is similar to EMT, but the prefactor is different. So the prefactor M here is different. Here it is given by EMT, and here is larger than that. But in addition to that, and more importantly, here we have, in the case of EMT, K vanishes when phi ZC goes to 0, but in our case, K vanishes for a finite value of phi ZC. As you can see here, it vanishes for a finite value of phi ZC. So we have to add here N, which is N. So N in our case is negative, and so we have here the vanishing of K at the finite phi ZC, which is actually the reminiscence of unjamming. So when we go down, here we are closer to the peak value, and then in the softening regime. That's why the data are not on this line. Here the system is globally unstable. So our maybe strain probe is too large for probing this. So we have some plastic deformation too. But if we use this data before the peak and extrapolate, we predict that phi ZC, K should vanish at some finite value of K, which is equal to minus N over M. And so this is nice because we know that in granular materials, we have this property. And for spheres, we have, of course, also the same behavior. Now, from the structure of the solutions in the EMT, we see that all of them are proportional to K. So if we divide the elastic moduli by K, we get something which depends only on the anisotropy. And here our data confirms this. So here are our data for different components here, different components, C11, C22, C55. We have a quite nice linear dependence on AC. Here, this is AC of all of the components, all of the elastic moduli. So this is for dodecahedra, this is for sphere, and this is EMT. And you see that, so we have, again, something which is correctly predicted by EMT is this linear dependence, but the coefficients here, RIG and SIG, are different. And so in general, if writing down, let's say, phenomenological expression, but inspired by EMT of the elastic moduli is this one. So it has a prefactor, which is our reference modulus, reference stress, let's say, an isotropic part depending only on ZC, and an anisotropic part depending only on AC. Here we have tabulated the coefficients for EMT and also our simulations of dodecahedra, ellipsohedra, and spheres. We also have put that for octahedra. But as you can see, some of these coefficients are very similar. For example, for R11 here, from EMT, we have 2.7, and in our case, it is 2.6, 2.5, 2.4. So you see that they are quite close. But for N, for example, as we have seen, this is 0 for EMT, but we have a finite negative value, as you can see here. So globally, if we have tabulated all these coefficients, it's very interesting. Why? Because they don't depend on friction coefficient. That's very interesting. And also, they don't evolve during triaxial compression. So if I know the shape, and if I can evaluate N, M, RIG, SIG, all these parameters, I don't use EMT anymore. I use these coefficients, which are given by simulations. Then I can predict basically the evolution of the elastic moduli as a function of ZC and AC. And so basically, friction coefficient affects the elastic moduli only through AC and ZC. So AC and ZC, of course, depend on the friction coefficient. And what is also interesting to learn from this expression is that higher values of elastic moduli in the case of polyhedra is not related to this coefficient. So this coefficient, of course, they explain part of the story, but they don't explain the higher value. By comparing the relative numerical values, see that higher value of elastic moduli in the case of polyhedra compared to spheres is mainly due to the higher values of ZC phi. So this is directly related to the microstructure. And now I show you again this. So these, now you can look at the solid lines. And here you have the elastic moduli, and the solid lines are predictions by this model. So we have just plugged the values of AC and ZC here, ZC and AC, yes. From simulations, we have the values of NM, RIJ, and SIJ, and we have calculated our CIJ at different points of the evolution of the system. And as you can see, it's nicely predicts the evolution of the elastic moduli. And now we can understand this wavy, sometimes wavy behavior. I mean, the fact that it's not strictly monotonous, the behavior is because, as you see here, we have a multiplicative expression. And we have seen that actually during this simulations, ZC is always decreasing and this is increasing. So when we multiply these two together, we get a curve which sometimes is decreasing and sometimes is increasing. So we can explain this wavy behavior of these predictions. And the worst predictions are here when we are approaching the peak, and after the peak, it's as we have seen, the data are actually deviating from a straight line. And the same for other coefficients. The last thing is that, as we know, the fact that EMT doesn't work, the effective medium theory doesn't work, is attributed to the fact that the displacements of particles are non-affine, or they have a non-affine component of displacement. And so that is a question. Why then these coefficients N, M, R, I, J, and so on are constant during a triaxial compression? We would have expected that they will change too. But if the non-affine effects are actually do not change much during a triaxial compression, then we can say it's normal, and it's normal that we have the same coefficients. There is nothing that can make them change. So we evaluated the non-affinity using the deviation of standard deviation, sorry, of relative displacements at the contact points. And so from that, we can measure the non-affinity, looking at the fluctuations actually, or variations of the displacements from a uniform displacement, from induced by the applied strain. And here you have the results. So you see that it is nearly 20%. So this is only for elastic props. It's not for plastic deformations. During the elastic probing, the value of C, the non-affinity, is 20% only. So 20% only of deformation is non-affine. And as you can see, interesting is that as a function of strain, you see that actually it's not changing much. Up to the peak point, well, it is increasing from 0.2 to 0.3 at most. And then, of course, it is increasing a lot because now we are sensitive to plastic deformations. The system is unstable, and so this is consistent with the fact that our data points, our elastic moduli, are deviating from the linear approximation. So that explains or physically justifies the fact that this model, simple model, is working. So I think it's time to conclude. So basically, we have evaluated the orthotropic elastic moduli for polyhedral particle packings for 4 values of coefficient of friction from the RCP state as the starting point. So we have 3 origins of elastic moduli. This reference value can change depending on the interaction. So, for example, if we have Hertzian contacts, we have to include into it the applied pressure. So in our case, because we have linear, it's simply Kn, the stiffness divided by D, but it can be different. We have an isotropic part depending only on the constraint number, and an anisotropic part which depends only on the contact orientation anisotropy. We have an analytical expression, and it is important, these 2 last points, that the effect of particle shape appears at 2 levels actually, through these parameters, which do not depend on friction, and secondly, through the microstructure. And here we see that if we know how microstructure is changing, I mean, what is the state in terms of the anisotropy and the connectivity of the network, we can predict the value of the values of the elastic moduli. And so we can probe it experimentally using waves, for example. So it means that by measuring the elastic moduli, we can actually evaluate the constraint number and the anisotropy of this packet. Okay, thank you very much for your attention.
Hey, Farhang, how's it going? I don't know, can you see me? Here. If I do this, the camera might look at me. Okay, no, I'm supposed to.
I see you.
Yeah, okay. I don't know. My voice pierces the air, so you'll probably figure out who I am even if you can't see me. Okay. So I have a question for you. So you're you've developed your, it's very nice, by the way. You developed your elastic theory based on the notion of sort of constant stiffness Hookean contact, right?
Yes.
So you have a Kn, a Kt. But I guess I'm struggling with this notion. For example, I know when you have face edge contact, there's no way that can be Hookean, right? Because as you press the edge into the face, the contact area is changing, right?
Yes.
Yeah,
Yes.
and also even if I have face-face contact, depending on how much face and how much face touch each other, I should get a different stiffness, right? But in your model, did you say that every one of these contacts has the same Kn?
Yes, that's the right question. So yes, we are assuming that we found that that is the easiest way actually, or maybe the most plausible way of doing, because when we change Kn, we introduce some instabilities into the system. You know, when face-face contact transforms, for example, by rotation into an edge-edge contact, if we change the values of the stiffnesses, you know,
Right.
it can induce local instabilities in the simulation. So we kept them as they are, and I agree with you. This is an approximation. Of course, you see that when we have a face-face contacts, we may have 10 contact points or even more. So we are taking all of them into account. But it means that the effective stiffness of a face-face contacts depends on the number of contact points that you introduce. But we hope that when we use ZC, so when we use only 3 degrees of freedom, then we get an evaluation of this, which is globally correct. But I agree with you; it should be tested, and that's why we introduced E star separately, because we say some of these aspects that you are mentioning can be captured into the value of E star.
Right. I just wonder how I wonder if there will always be an E star, or whether if you let the contacts be varying enough, you won't get a nice separation anymore. Right. Like if you've got lots of different kinds of contact, it was nice that E star came out, but I feel like some of that came from the fact that you had constant Hookean contacts. Right.
Yeah.
Yeah. Okay. Very cool.
Well, you know, anyway, we can't use Hertz because we don't have, well-defined curvatures. In the model we have because these are spheropolyhedral. So we can use the expressions of, local laws, elastic laws of between 2 cylinders, for example.
Yeah. There are contact theories for wedge on face. And they're pretty
Yes.
The contact stiffness changes with compression,
That can be done. That can be an improvement. Yeah.
Hi, Farhang. I don't have a piercing voice like Ken, but I have a strong accent, and I'm sure you recognize me too.
Oh, sure. How are you?
To see you, and sorry that you couldn't come. Thanks for making time. I have a more technical question because I didn't understand the meaning of the probing that you do, the small little strains. But it seems like you're plotting it during strain. So I don't think you clarified. Do you probe it while or do you freeze the sample? And what about the granular temperature? It's hard for me to imagine that if you stop at any given moment and do a probing, there won't be any relaxation of the system, even if you go super slow shear rate. So can you clarify that, please?
Yes. Thank you for mentioning this. We have to, that's what makes it difficult. Actually, it takes time because we have to stop the simulation or take a configuration. At that point, we have to wait to relax and then apply the small strain probe. So that's exactly what you are saying. So
in fact, the stress relaxes during that time. And you take that into account. Okay, cool.
Yeah, that's true. That's true. And we hope that for this relaxation, actually, the structure doesn't change. So,
can I follow up? Because of the way you do this, at every instant, it is basically a spring network when you're calculating this, right? Do you really even need to use your simulation to calculate this, or could you do something like on the side offline that mimics the spring network from your simulation, and you just probe that, and then you don't have to worry about anything?
Yeah, we can do that. I mean, we can use the matrix.
You wouldn't have to worry about sliding or anything like that. Yeah.
That's basically which can be done. I mean,
Yeah.
Jean-Noël Roux did that. He used this method. We probed, but it can be done. We can use vibration spectra and things like that. So yeah.
Let someone else.
Yeah, no, okay.
Hey, guess who it is? Am I right that you never consider edge-edge contact?
They are.
I thought you did. In your picture, you showed three. You had face, 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 edge, face, vertex, right?
Yes.
Do you do edge, edge?
Yeah, we also have edge, but like this, not this.
Yeah, of course. Okay. Okay. That's fine.
Yeah, they are. But what is interesting is that you have only 4 types of contacts.
Four times.
That covers all possibilities for interactions between 2 polyhedra. Yeah.
Any other questions? Okay. It comes to thank Farhang again.
Thank you very much. Thank you.